Chapter 9. Aircraft Electrical System. Introduction. The satisfactory performance of any modern aircraft depends to a very great degree on the continuing reliability of electrical systems and subsystems. Improperly or carelessly installed or maintained wiring can be a source of both immediate and potential danger. The continued proper performance of electrical systems depends on the knowledge and technique of the mechanic who installs, inspects, and maintains the electrical system wires and cables. 9-1. I equals, R equals, R equals, I equals, R equals. Ohm's law. Ohm's law describes the basic mathematical relationships of electricity. The law was named after German physicist George Simon Ohm, 1789-1854. Basically, Ohm's law states that the current, electron flow, through a conductor is directly proportional to the voltage, electrical pressure, applied to that conductor and inversely proportional to the resistance of the conductor. The unit used to measure resistance is called the ohm. The symbol for the ohm is the Greek letter omega. In mathematical formulas, the capital letter R refers to resistance. The resistance of a conductor and the voltage applied to it determine the number of amperes of current flowing through the conductor. Thus, 1 ohm of resistance limits the current flow to 1 ampere in a conductor to which a voltage of 1 volt is applied. The primary formula derived from Ohm's law is E equals I times R. E equals electromotive force measured in volts, I equals current flow measured in amps, and R equals resistance measured in ohms. This formula can also be written to solve for current or resistance. ER, EI. Ohm's law provides a foundation of mathematical formulas that predict how electricity responds to certain conditions. Figure 9-1 for example, Ohm's law can be used to calculate that a lamp of 12 ohms passes a current of 2 amps when connected to a 24-volt direct current, DC, power source. Example 1. A 28-volt landing light circuit has a lamp with 4 ohms of resistance. Calculate the total current of the circuit. R equals 12. I equals 2A. E equals 24 VDC. Figure 9-1. Ohm's law used to calculate how much current the lamp will pass when connected to a 24-volt DC power source. ER, 28 volts. I equals 4. I equals 7 amps. Example 2. A 28-volt DI-spoot circuit has a current of 6.5 amps. Calculate the resistance of the DI-spoot. EI, 28 volts 6.5 amps. R equals 4.31. Example 3. A taxi light has a resistance of 4.9 and a total current of 2.85 amps. Calculate the system voltage. E equals I times R. E equals 2.85 times 4.9. E equals 14 volts. Whenever troubleshooting aircraft electrical circuits, it is always valuable to consider Ohm's law. A good understanding of the relationship between resistance and current flow can help one determine if a circuit contains an open or a short. Remembering that a low resistance means increased current can help explain why circuit breakers pop or fuses blow. In almost all cases, aircraft loads are wired in parallel to each other, therefore, there is a constant voltage supplied to all loads, and the current flow through a load is a function of that load's resistance. Figure 9-2 illustrates several ways of using Ohm's law for the calculation of current, voltage, and resistance. Current. Electrical current is the movement of electrons. This electron movement is referred to as current flow or current flow. In practical terms, this movement of electrons must take place within a conductor, wire. Current is typically measured in amps. The symbol for current is I, and the symbol for amps is A. The current flow is actually the movement of the free electrons found within conductors. Common conductors. 9-2. A. Defined I, amperes, place thumb over I and divide E by R as indicated. E. IXR. B. Defined R, ohms, place thumb over R and divide as indicated. E. IXR. C. Defined E, volts, place thumb over E and multiply as indicated. E. IXR. Figure 9-2. Ohm's law chart. Include copper, silver, aluminum, and gold. The term free electron describes a condition in some atoms where the outer electrons are loosely bound to their parent atom. These loosely bound electrons are easily motivated to move in a given direction when an external source, such as a battery, is applied to the circuit. These electrons are attracted to the positive terminal of the battery, while the negative terminal is the source of the electrons. So, the measure of current is actually the number of electrons moving through a conductor in a given amount of time. The internationally accepted unit for current is the ampere, A. 1 ampere, A, of current is equivalent to 1 coulomb, C, of charge passing through a conductor in 1 second. 1 coulomb of charge equals 6.28 times 1018 electrons. Obviously, the unit of amperes is a much more convenient term to use than coulombs. The unit of coulombs is simply too small to be practical. When current flows in one direction, it is called direct current, DC. Later in the text, the form of current that periodically oscillates back and forth within the circuit is discussed. The present discussion is concerned only with the use of DC. It should be noted that, as with the movement of any mass, electron movement, current flow only occurs when there is a force present to push the electrons. This force is commonly called voltage, described in more detail in the next section. When a voltage is applied across the conductor, an electromotive force creates an electric field within the conductor, and a current is established. The electrons do not move in a straight direction, but undergo repeated collisions with other nearby atoms within a conductor. These collisions usually knock other free electrons from their atoms, and these electrons move on toward the positive end of the conductor with an average velocity called the drift velocity, which is relatively low speed. To understand the nearly instantaneous speed of the effect of the current, it is helpful to visualize a long tube filled with steel balls. Figure 9-3. It can be seen that a ball introduced in one end of the tube, which represents the conductor, immediately causes a ball to be emitted at the opposite end of the tube. Thus, electric current can be viewed as instantaneous, even though it is the result of a relatively slow drift of electrons. Conventional current theory and electron theory. There are two competing schools of thought regarding the flow of electricity. The two explanations are the conventional current theory and the electron theory. Both theories describe the movement of electrons through a conductor. They simply explain the direction current moves. Typically during troubleshooting or the connection of electrical circuits, the use of either theory can be applied, as long as it is used consistently. The Federal Aviation Administration, FAA, officially defines current flow using electron theory, negative to positive. The conventional current theory was initially advanced by Benjamin Franklin, who reasoned that current flowed out of a positive source into a negative source or an area that lacked an abundance of charge. The notation assigned to the electric charges was positive, plus, for the abundance of charge, and negative, for a lack of charge. It then seemed natural to visualize the flow of current as being from the positive, plus, to the negative. Later discoveries were made that proved that just the opposite is true. Electron theory describes what actually happens in the case of an abundance of electrons flowing out of the negative source to an area that lacks. Figure 9-3. Electron flow. 9-3. Electrons are the positive, plus, source. Both conventional flow and electron flow are used in industry. Electromotive force, voltage. Voltage is most easily described as electrical pressure force. It is the electromotive force, EMF, or the push or pressure from one end of the conductor to the other, that ultimately moves the electrons. The symbol for EMF is the capital letter E. EMF is always measured between 2 points and voltage is considered a value between 2 points. For example, across the terminals of the typical aircraft battery, voltage can be measured as the potential difference of 12 volts or 24 volts. That is to say that between the two terminal posts of the battery, there is a voltage available to push current through a circuit. Free electrons in the negative terminal of the battery move toward the excessive number of positive charges in the positive terminal. The net result is a flow or current through a conductor. There cannot be a flow in a conductor unless there is an applied voltage from a battery, generator, or ground power unit. The potential difference, or the voltage across any 2 points in an electrical system, can be determined by V1 V2 equals V drop. Example: the voltage at one point is 14 volts. The voltage at a second point in the circuit is 12.1 volts. To calculate the voltage drop, use the formula above to get a total voltage drop of 1.9 volts. Figure 9-4 illustrates the flow of electrons of electric current. Two interconnected water tanks demonstrate that, when a difference of pressure exists between the two tanks, water flows until the two tanks are equalized. Figure 9-4 shows the level of water in tank A to be at a higher level, reading 10 pounds per square inch, psi, higher potential energy, and the water level in tank B, reading 2 psi, lower potential energy. Between the two tanks, there is 8 psi potential difference. If the valve in the interconnecting line between the tanks is opened, water flows from tank A into tank B until the level of water, potential energy, of both tanks is equalized. It is important to note that it was not the pressure in tank A, B, figure 9-4, difference of pressure, that caused the water to flow. Rather, it was the difference in pressure between tank A and tank B that caused the flow. This comparison illustrates the principle that electrons move, when a path is available, from a point of excess electrons, higher potential energy, to a point deficient in electrons, lower potential energy. The force that causes this movement is the potential difference in electrical energy between the 2 points. This force is called the electrical pressure, voltage, the potential difference, or the electromotive force, electron moving force. Resistance. The two fundamental properties of current and voltage are related by a third property known as resistance. In any electrical circuit, when voltage is applied to it, a current results. The resistance of the conductor determines the amount of current that flows under the given voltage. In general, the greater the circuit resistance, the less the current. If the resistance is reduced, then the current will increase. This relation is linear in nature and is known as Ohm's law. An example would be if the resistance of a circuit is doubled, and the voltage is held constant, then the current through the resistor is cut in half. There is no distinct dividing line between conductors and insulators. Under the proper conditions, all types of material conduct some current. Materials offering a resistance to current flow midway between the best conductors and the poorest conductors, insulators, are sometimes referred to as semiconductors, and find their greatest application in the field of transistors. The best conductors are materials, chiefly metals, that possess a large number of free electrons. Inversely, insulators are materials having few free electrons. The best conductors are silver, copper, gold, and aluminum, but some nonmetals, such as carbon and water, can be used as conductors. Materials such as rubber, glass, ceramics, and plastics are such poor conductors that they are usually used as insulators. The current flow in some of these materials is so low that it is usually considered zero. Factors affecting resistance. The resistance of a metallic conductor is dependent on the type of conductor material. It has been pointed out that certain metals are commonly used as conductors because of the large number of free electrons in their outer orbits. Copper is usually considered the best available conductor material, since a copper wire of a particular diameter offers a lower resistance to current flow than an aluminum wire of the same diameter. However, aluminum is much lighter than copper, and for this reason, as well as cost considerations, aluminum is often used when the weight factor is important. 9-4. The resistance of a metallic conductor is directly proportional to its length. The longer the length of a given size of wire, the greater the resistance. Figure 9-5 shows two wire conductors of different lengths. If 1 volt of electrical pressure is applied across the two ends of the conductor that is 1 foot in length, and the resistance to the movement of free electrons is assumed to be 1 ohm, the current flow is limited to 1 ampere. If the same size conductor is doubled in length, the same electrons set in motion by the 1 volt applied now find twice the resistance. Electromagnetic generation of power. Electrical energy can be produced through a number of methods. Common methods include the use of light, pressure, heat, chemical, and electromagnetic induction. Of these processes, electromagnetic induction is most responsible for the generation of the majority of the electrical power used by humans. Virtually all mechanical devices, generators and alternators, that produce electrical power employ the process of electromagnetic induction. The use of light, pressure, heat, and chemical sources for electrical power is found on aircraft, but produce a minimal amount of all the electrical power consumed during a typical flight. In brief, light can produce electricity using a solar cell, photovoltaic cell. These cells contain a certain chemical that converts light energy into voltage/current. Using pressure to generate electrical power is commonly known as the piezoelectric effect. The piezoelectric effect, piezo or pi is taken from Greek. To press, pressure, to squeeze, is a result of the application of mechanical pressure on a dielectric or non-conducting crystal. Chemical energy can be converted into electricity, most commonly in the form of a battery. A primary battery produces electricity using two different metals in a chemical solution like alkaline electrolyte. A chemical reaction exists between the metals which frees more electrons in one metal than in the other. Heat used to produce electricity creates the thermoelectric effect. When a device called a thermocouple is subjected to heat, a voltage is produced. A thermocouple is a junction between two different metals that produces a voltage related to a temperature difference. If the thermocouple is connected to a complete circuit, a current also flows. Thermocouples are often found on aircraft as part of a temperature monitoring system, such as a cylinder head temperature gauge. Electromagnetic induction is the process of producing a voltage, EMF, by moving a magnetic field in relationship to a conductor. As shown in figure 9-6, when a conductor, wire, is moved through a magnetic field, an EMF is produced in the conductor. If a complete circuit is connected to the conductor, the voltage also produces a current flow. One single conductor does not produce significant voltage/current via electromagnetic induction. Figure 9-6 in practice, instead of a single wire, a coil of wire is moved through the magnetic field of a strong magnet. This produces a greater electrical output. In many cases, the magnetic field is created by using a powerful electromagnet. This allows for the production of a greater voltage/current due to the stronger magnetic field produced by the electromagnet when compared to an ordinary magnet. Please note that this text often refers to voltage/current in regards to electrical power. Remember, voltage, electrical pressure, must be present to produce a current, electron flow. Hence, the output energy generated through the process of electromagnetic induction always consists of voltage. EMF, 2 feet, 0.5 amp, 2 ohms, 1 foot, plus, 1 amp, 1 ohm. Figure 9-5. Resistance varies with length of conductor. Sn. Motion of conductor. Figure 9-6. Inducing an EMF in a conductor. 9-5. Current also results when a complete circuit is connected to that voltage. Electrical power is produced when there is both electrical pressure E, EMF, and current, I. Power equals current times voltage, P equals I times E. It is the relative motion between a conductor and a magnetic field that causes current to flow in the conductor. Either the conductor or magnet can be moving or stationary. When the magnet and its field are moved through a coiled conductor, as shown in figure 9-7, a DC voltage with a specific polarity is produced. The polarity of this voltage depends on the direction in which the magnet is moved, and the position of the north and south poles of the magnetic field. The generator left-hand rule can be used to determine the direction of motion of magnet galvanometer. Current flow within the conductor. Figure 9-8. Of course, the direction of current flow is a function of the polarity of the voltage induced into the conductor. In practice, reducing voltage/current using the process of electromagnetic induction requires a rotating machine. Generally speaking, on all aircraft, a generator or alternator employs the principles of electromagnetic induction to create electrical power for the aircraft. Either the magnetic field can rotate, or the conductor can rotate. Figure 9-9 The rotating component is driven by a mechanical device, such as an aircraft engine. During the process of electromagnetic induction, the value of the induced voltage/current depends on three basic factors. 1. Number of turns in the conductor coil. More loops equals greater induced voltage. I. A. N. Inductor moved up. Flux forward. Coil. S. I. Inducted EMF. B. N. Magnet at rest. NS. Induced EMF. S. Figure 9-8. An application of the generator left-hand rule. N. Motion of magnet. C. S. I. SN. A. B. I. Figure 9-7. Inducing a current flow. 9-6. Figure 9-9. Voltage induced in a loop. 2. Strength of the electromagnet. The stronger the magnetic field, the greater the induced voltage. 3. Speed of rotation of the conductor or magnet. The faster the rotation, the greater the induced voltage. Figure 9-10 illustrates the basics of a rotating machine used to produce voltage. The simple generating device consists of a rotating loop, marked A and B, placed between two magnetic poles, N and S. The ends of the loop are connected to two metal slip rings, collector rings, C1 and C2. Current is taken from the collector rings by brushes. If the loop is considered as separate wires, A and B, and the left-hand rule for generators is applied, then it can be observed that as wire B moves up across the field, a voltage is induced that causes the current to flow towards the reader. As wire A moves down across the field, a voltage is induced that causes the current to flow away from the reader. When the wires are formed into a loop, the voltages induced in the two sides of the loop are combined. Therefore, for explanatory purposes, the action of either conductor, or B, while rotating in the magnetic field, is similar to the action of the loop. Figure 9-11 illustrates the generation of alternating current, AC, with a simple loop conductor rotating in a magnetic field. As it is rotated in a counterclockwise direction, varying voltages are induced in the conductive loop. Position 1. The conductor A moves parallel to the lines of force. Since it cuts no lines of force, the induced voltage is 0. As the conductor advances from position 1 to position 2, the induced voltage gradually increases. Position 2 The conductor is now moving in a direction perpendicular to the flux, and cuts a maximum number of lines of force. Therefore, a maximum voltage is induced. As the conductor moves beyond position 2, it cuts a decreasing amount of flux, and the induced voltage decreases. Position 3 At this point, the conductor has made half a revolution, and again moves parallel to the lines of force, and no voltage is induced in the conductor. As the A conductor passes position 3, the direction of induced voltage now reverses since the A conductor is moving downward, cutting flux in the opposite direction. As the A conductor moves across the south pole, the induced voltage gradually increases in the negative direction until it reaches position 4. Position 4 Like position 2, the conductor is again moving perpendicular to the flux, and generates a maximum negative voltage. From position 4 to position 5, the induced voltage gradually decreases until the voltage is 0, and the conductor and wave are ready to start another cycle. Position 5. The curve shown at position 5 is called a sine wave. It represents the polarity and the magnitude of the instantaneous. N. Cross-section of loop. N. Direction of rotation. Brushes. B. A. C1. C2. Plus. A B. Direction of movement of the loop through the magnetic field. Collector rings. S. S. A B. Side of loop current flow is toward the reader, current flow is away from reader plus. Figure 9-10. Simple generator. 9-7. Magnetic field. N. B. C1 C2. A. 360 degrees. 0 degrees 90 degrees 180 degrees 270 degrees. N. A. C1 C2. 360 degrees. 0 degrees 90 degrees 180 degrees 270 degrees. B. S. 0 voltage. Position 1 Position 2. S. Maximum positive voltage. Rotating conductors moving parallel to magnetic field, cutting minimum lines of force. Quarter turn completed. Conductors cutting directly across the magnetic field as conductor A passes across the north magnetic pole and B passes across the S pole. N. A. 360 degrees. 0 degrees 90 degrees 180 degrees 270 degrees. N. B. C1 C2. B. C1 C2. A. 360 degrees. 0 degrees 90 degrees 180 degrees 270 degrees. S. S. Voltage drops to 0. Maximum negative voltage. Position 3. 1/2 turn completed. Conductor again moving parallel to magnetic field, cutting minimum lines of force. Position 4. 3/4 turn completed. Conductors again moving directly across magnetic field. A passes across south magnetic pole and B across N magnetic pole. N, B, C1, C2, A, 360 degrees, 0 degrees, 90 degrees, 180 degrees, 270 degrees. S, 0 voltage. Position 5. Full turn completed. Conductor A has made one complete cycle and is in same position as in position A. The generator has generated one complete cycle of alternating voltage or current. Figure 9-11. Generation of a sine wave. Values of the voltages generated. The horizontal baseline is divided into degrees, or time, and the vertical distance above or below the baseline represents the value of voltage at each particular point in the rotation of the loop. The specific operating principles of both alternators and generators as they apply to aircraft is presented later in this text. 9-8. Alternating current, AC, introduction. Alternating current, AC, electrical systems are found on most multi-engine, high-performance turbine-powered aircraft and transport category aircraft. AC is the same type of electricity used in industry and to power our homes. Direct current, DC, is used on systems that must be compatible with battery power, such as on light aircraft and automobiles. There are many benefits of AC power when selected over DC power for aircraft electrical systems. AC can be transmitted over long distances more readily and more economically than DC, since AC voltages can be increased or decreased by means of transformers. Because more and more units are being operated electrically in airplanes, the power requirements are such that a number of advantages can be realized by using AC, especially with large transport category aircraft. Space and weight can be saved since AC devices, especially motors, are smaller and simpler than DC devices. In most AC motors, no brushes are required, and they require less maintenance than DC motors. Circuit breakers operate satisfactorily under loads at high altitudes in an AC system, whereas arcing is so excessive on DC systems that circuit breakers must be replaced frequently. Finally, most airplanes using a 24-volt DC system have special equipment that requires a certain amount of 400-cycle AC current. For these aircraft, a unit called an inverter is used to change DC to AC. Inverters are discussed later in this book. AC is constantly changing in value and polarity, or as the name implies, alternating. Figure 9-12 shows a graphic comparison of DC and AC. The polarity of DC never changes, and the polarity and voltage constantly change in AC. It should also be noted that the AC cycle repeats at given intervals. With AC, both voltage and current start at 0, increase, reach a peak, then decrease and reverse polarity. If one is to graph this concept, it becomes easy to see the alternating waveform. This waveform is typically referred to as a sine wave. Definitions. Values of AC. There are 3 values of AC that apply to both voltage and current. These values help to define the sine wave, and are called instantaneous, peak, and effective. It should be noted that during the discussion of these terms, the text refers to voltage. But remember, the values apply to voltage and current in all AC circuits. Instantaneous. An instantaneous voltage is the value at any instant in time along the AC wave. The sine wave represents a series of these values. The instantaneous value of the voltage varies from 0 at 0 degrees to maximum at 90 degrees, back to 0 at 180 degrees, to maximum in the opposite direction at 270 degrees, and to 0 again at 360 degrees. Any point on the sine wave is considered the instantaneous value of voltage. Peak. The peak value is the largest instantaneous value, often referred to as the maximum value. The largest single positive value occurs after a certain period of time when the sine wave reaches 90 degrees, and the largest single negative value occurs when the wave reaches 270 degrees. Although important in the understanding of the AC sine wave, peak values are seldom used by aircraft technicians. Effective. The effective values for voltage are always less than the peak, maximum, values of the sine wave and approximate DC voltage of the same value. For example, an AC circuit of 24 volts and 2 amps should produce the same heat through a resistor as a DC circuit of 24 volts and 2 amps. The effective value is also known as the root mean square, or RMS value, which refers to the mathematical process by which the value is derived. Waveform for DC. Waveform for AC. Volts. Volts plus. 180 degrees, 270 degrees, 360 degrees. 0 degrees, 90 degrees. Closed switch. Operation of circuit. Time. Open switch. Time. Figure 9-12. DC and AC voltage curves. 9-9. Most AC meters display the effective value of the AC. In almost all cases, the voltage and current ratings of a system or component are given in effective values. In other words, the industry ratings are based on effective values. Peak and instantaneous values, used only in very limited situations, would be stated as such. In the study of AC, any values given for current or voltage are assumed to be effective values unless otherwise specified. In practice, only the effective values of voltage and current are used. The effective value is equal to 0.707 times the peak maximum value. Inversely, the peak value is 1.41 times the effective value. Thus, The 110 volt value given for AC is only 0.707 of the peak voltage of this supply. The maximum voltage is approximately 155 volts. 110 times 1.41 equals 155 volts maximum. How often the AC waveform repeats is known as the AC frequency. The frequency is typically measured in cycles per second, CPS, or Hertz, Hz. 1 Hz equals 1 CPS. The time it takes for the sine wave to complete one cycle is known as period, P. Period is a value or time period and typically measured in seconds, milliseconds, or microseconds. It should be noted that the time period of a cycle can change from one system to another. It is always said that the cycle completes in 360 degrees, related to the 360 degrees of rotation of an AC alternator. Figure 9-13. Cycle defined. A cycle is a completion of a pattern. Whenever a voltage or current passes through a series of changes, returns to the starting point, and then repeats the same series of changes, the series is called a cycle. When the voltage values are graphed, as in figure 9-14, the complete AC cycle is displayed. One complete cycle is often referred to as the sine wave, and said to be 360 degrees. It is typical to start the sine wave, where the voltage is 0. The voltage then increases to a maximum positive value, decreases to a value of 0 then. Positive alternation. Vertical scale, voltage. Horizontal scale, time. 1t, 2t, 3t, 4t. Negative alternation. One cycle, one period, time, one wavelength, distance. Second cycle. Figure 9-14. Cycle of voltage. Increases to a maximum negative value, and again decreases to 0. The cycle repeats until the voltage is no longer available. There are two alternations in a complete cycle. The positive alternation and the negative. It should be noted that the polarity of the voltage reverses for each half cycle. Therefore, during the positive half cycle, the electron flow is considered to be in one direction. During the negative half cycle, the electrons reverse direction and flow the opposite way through the circuit. Frequency defined. The frequency is the number of cycles of AC per second, CPS. The standard unit of frequency measurement is the Hz. Figure 9-15. In a generator, the voltage and current pass through a complete cycle of values each time a coil or conductor passes under a north and south pole of the magnet. The number of cycles for each revolution of the coil or conductor is equal to the number of pairs of poles. Plus 0. Average value. RMS value. Average equals 0.637 peak RMS. Effective equals 0.707 peak. Peak to peak equals 2 peaks. Peak value. Peak to peak value. 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. 1t. 1 second frequency equals 2 cycles per second. 90 degrees. 180 degrees. 0 degrees. 360 degrees. 270 degrees. 1 second frequency equals 8 cycles per second. Figure 9-13. Values of AC. 9-10. Figure 9-15. Frequency in cycles per second. The frequency, N, is equal to the number of cycles in one revolution multiplied by the number of revolutions per second. Period defined. The time required for a sine wave to complete one full cycle is called a period, P. A period is typically measured in seconds, milliseconds, or microseconds. Figure 9-14. The period of a sine wave is inversely proportional to the frequency. That is to say, that the higher the frequency, the shorter the period. The mathematical relationship between frequency and period is given as period E equals 1f. Frequency f equals 1 e. Wavelength defined. The distance that a waveform travels during a period is commonly referred to as a wavelength, and is indicated by the Greek letter lambda. Wavelength is related to frequency by the formula wave speed equals wavelength frequency. The higher the frequency is, the shorter the wavelength is. The measurement of wavelength is taken from one point on the waveform to a corresponding point on the next waveform. Figure 9-14. Since wavelength is a distance, common units of measure include meters, centimeters, millimeters, or nanometers. For example, a sound wave of frequency 20 Hz would have wavelength of 17 meters, and a visible red light wave of 4.3 times 1012 Hz would have a wavelength of roughly 700 nanometers. Keep in mind that the actual wavelength depends on the media through which the waveform must travel. Phase relationships. Phase is the relationship between two sine waves, typically measured in angular degrees. For example, if there are two different alternators producing power, it would be easy to compare their individual sine waves and determine their phase relationship. In figure 9-16b, there is a 90 degrees phase difference between the two voltage waveforms. A phase relationship can be between any two sine waves. The phase relationship can be measured between two voltages of different alternators, or the current and voltage produced by the same alternator. Voltage. Current. 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. A. Voltage and current are in phase. Voltage source 1, lead source 2. Voltage source 2, lag source 1. 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. B. 2 voltage waves, 90 degrees out of phase. Voltage source 1. Voltage source 2. 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. C. 2 voltage waves, 180 degrees out of phase. Figure 9-16. In phase and out of phase conditions. Figure 9-16a shows a voltage signal and a current signal superimposed on the same time axis. Notice that when the voltage increases in the positive alternation, that the current also increases. When the voltage reaches its peak value, so does the current. Both waveforms then reverse and decrease back to a zero magnitude, and proceed in the same manner in the negative direction as they did in the positive direction. When two waves are exactly in step with each other, they are said to be in phase. To be in phase, the two waveforms must go through their maximum and minimum points at the same time, and in the same direction. 9-11. When two waveforms go through their maximum and minimum points at different times, a phase difference exists between the two. In this case, the two waveforms are said to be out of phase with each other. The terms lead and lag are often used to describe the phase difference between waveforms. The waveform that reaches its maximum or minimum value first is said to lead the other waveform. Figure 9-16b shows this relationship. On the other hand, the second waveform is said to be lagging the first source. When a waveform is said to be leading or lagging, the difference in degrees is usually stated. If the two waveforms differ by 360 degrees, they are said to be in phase with each other. If there is a 180 degrees difference between the two signals, then they are still out of phase, even though they are both reaching their minimum and maximum values at the same time. Figure 9-16c. Opposition to current flow of AC. There are three factors that can create an opposition to the flow of electrons, current, in an AC circuit. Resistance, similar to resistance of DC circuits, is measured in ohms, and has a direct influence on AC regardless of frequency. Inductive reactance and capacitive reactance, on the other hand, oppose current flow only in AC circuits, not in DC circuits. Since AC constantly changes direction and intensity, inductors and capacitors may also create an opposition to current flow in AC circuits. It should also be noted that inductive reactance and capacitive reactance may create a phase shift between the voltage and current in an AC circuit. Whenever analyzing an AC circuit, it is very important to consider the resistance, inductive reactance, and the capacitive reactance. All three have an effect on the current of that circuit. Resistance. As mentioned, resistance creates an opposition to current in an AC circuit similar to the resistance of a DC circuit. The current through a resistive portion of an AC circuit is inversely proportional to the resistance, and directly proportional to the voltage applied to that circuit or portion of the circuit. The equations I equals E/R and D equals I times R show how current is related to both voltage and resistance. It should be noted that resistance in an AC circuit does not create a phase shift between voltage and current. Figure 9-17 shows how a circuit of 10 ohms allows 11.5 amps of current flow through an AC resistive circuit of 115 volts. I equals ER. I equals 115 V. 10. I equals 11.5 amps. R equals 10. 115 VAC. A. Ammeter I equals 11.5 A. Figure 9-17. Resistance. Inductive reactance. When moving a magnet through a coil of wire, a voltage is induced across the coil. If a complete circuit is provided, then a current will also be induced. The amount of induced voltage is directly proportional to the rate of change of the magnetic field with respect to the coil. Inversely, current flowing through a coil of wire produces a magnetic field. When this wire is formed into a coil, it then becomes a basic inductor. The primary effect of a coil is its property to oppose any change in current through it. This property is called inductance. When current flows through any conductor, a magnetic field starts to expand from the center of the wire. As the lines of magnetic force go outward through the conductor, they induce an EMF in the conductor itself. The induced voltage is always in the direction opposite to the direction of the applied current flow. The effects of this countering EMF are to oppose the applied current. This effect is only a temporary condition. Once the current reaches a steady value in the conductor, the lines of magnetic force are no longer expanding, and the countering EMF is no longer present. Since AC is constantly changing in value, the inductance repeats in a cycle always opposite the applied voltage. It should be noted that the unit of measure for inductance is the Henry, H. The physical factors that affect inductance are 1. Number of turns. Doubling the number of turns in a coil produces a field twice as strong if the same current is used. As a general rule, the inductance varies with the square of the number of turns. 2. Cross-sectional area of the coil. The inductance of a coil increases directly as the cross-sectional area of the core increases. Doubling the radius of a coil increases the inductance by a factor of 4. 3. Length of a coil. Doubling the length of a coil, while keeping the same number of turns, reduces inductance by 1/2. 9-12. 4. Core material around which the coil is formed. Coils are wound on either magnetic or non-magnetic materials. Some non-magnetic materials include air, copper, plastic, and glass. Magnetic materials include nickel, iron, steel, and cobalt, which have a permeability that provides a better path for the magnetic lines of force and permit a stronger magnetic field. Since AC is in a constant state of change, the magnetic fields within an inductor are also continuously changing and create an inducted voltage/current. This induced voltage opposes the applied voltage and is known as the counter EMF. This opposition is called inductive reactance, symbolized by XL, and is measured in ohms. This characteristic of the inductor may also create a phase shift between voltage and current of the circuit. The phase shift created by inductive reactance always causes voltage to lead current. That is, the voltage of an inductive circuit reaches its peak values before the current reaches peak values. Additional discussions related to phase shift are presented later in this chapter. Inductance is the property of a circuit to oppose any change in current and is measured in henries. Inductive reactance is a measure of how much the countering EMF in the circuit opposes the applied current. The inductive reactance of a component is directly proportional to the inductance of the component and the applied frequency to the circuit. By increasing either the inductance or applied frequency, the inductive reactance likewise increases and presents more opposition to current in the circuit. This relationship is given as XL equals 2FL, where XL equals inductive reactance in ohms, L equals inductance in henries, F equals frequency in cycles per second, and equals 3.1416. In figure 9-18, an AC series circuit is shown in which the inductance is 0.146 Henry and the voltage is 110 volts at a frequency of 60 cycles per second. Inductive reactance is determined by the following method. XL equals 2 times F times L. XL equals 6.28 times 60 times 0.146. XL equals 55. In AC series circuits, inductive reactance is added like resistances in series in a DC circuit. Figure 9-19, the total reactance in the illustrated circuit equals the sum of the individual reactances. L equals 0.146H, 110 VAC 60HZ. A. Figure 9-18. AC circuit containing inductance. XL equals XL1 plus XL2. XL equals 10 plus 15. XLT equals 25. The total reactance of inductors connected in parallel is found the same way as the total resistance in a parallel circuit. Figure 9-20 thus, the total reactance of inductances connected in parallel, as shown, is expressed as XLT equals 1, 1 plus 1 plus 1, XL1, XL2, XL3, XLT equals 1, 1 plus 1 plus 1, 15, 15, 15, XLT equals 5, XL1 equals 10, AC power supply, XL2 equals 15. Figure 9-19, inductances in series, 9-13. XL1 equals 15, XL2 equals 15, XL3 equals 15. Dielectric. AC power supply, 80 μF capacitor. AC generator 110 V at 400 CPS. XY. Figure 9-20. Inductances in parallel. Figure 9-21. Capacitor in an AC circuit. Capacitive reactance. Capacitance is the ability of a body to hold an electric charge. In general, a capacitor is constructed of two parallel plates separated by an insulator. The insulator is commonly called the dielectric. The capacitor's plates have the ability to store electrons when charged by a voltage source. The capacitor discharges when the applied voltage is no longer present and the capacitor is connected to a current path. In an electrical circuit, a capacitor serves as a reservoir or storehouse for electricity. The basic unit of capacitance is the farad and is given by the letter F. By definition, 1 farad is 1 coulomb of charge stored with 1 volt across the plates of the capacitor. In practical terms, 1 farad is a large amount of capacitance. Typically, in electronics, much smaller units are used. The two more common smaller units are the microfarad, F, which is 10-6 farad, and the picofarad, PF, which is 10-12 farad. Capacitance is a function of the physical properties of the capacitor. 1. The capacitance of parallel plates is directly proportional to their area. A larger plate area produces a larger capacitance, and a smaller area produces less capacitance. If we double the area of the plates, there is room for twice as much charge. 2. The capacitance of parallel plates is inversely proportional to the distance between the plates. 3. The dielectric material affects the capacitance of parallel plates. The dielectric constant of a vacuum is defined as 1, and that of air is very close to 1. These values are used as a reference, and all other materials have values relative to that of air, vacuum. When an AC is applied in the circuit, the charge on the plates constantly changes. Figure 9-21. This means that electricity must flow first from Y clockwise around to X, and from X counterclockwise around to Y, and from Y clockwise around to X, and so on. Although no current flows through the insulator between the plates of the capacitor, it constantly flows in the remainder of the circuit between X and Y. As this current alternates to and from the capacitor, a certain time lag is created. When the capacitor charges or discharges through a resistance, a certain amount of time is required for a full charge or discharge. The voltage across the capacitor does not change instantaneously. The rate of charging or discharging is determined by the time constant of the circuit. This rate of charge and discharge creates an opposition to current flow in AC circuits known as capacitive reactance. Capacitive reactance is symbolized by Xc and is measured in ohms. This characteristic of a capacitor may also create a phase shift between voltage and current of the circuit. The phase shift created by capacitive reactance always causes current to lag voltage. That is, the current of a capacitive circuit reaches its peak values before the voltage reaches peak values. Capacitive reactance is a measure of how much the capacitive circuit opposes the applied current flow. Capacitive reactance is measured in ohms. The capacitive reactance of a circuit is indirectly proportional to the capacitance of the circuit and the applied frequency to the circuit. By increasing either the capacitance or applied frequency, the capacitive reactance decreases, and vice versa. This relationship is given as 1. Xc equals 2 Fc, where Xc equals capacitive reactance in ohms, C equals capacitance in farads, F equals frequency in cycles per second, and equals 3.1416. In figure 9-21, a series circuit is shown in which the applied voltage is 110 volts at 400 CPS, and the capacitance of a condenser is 80 mF. Find the capacitive reactance and the current flow. To find the capacitive reactance, the following equation. 1. Xc equals 2 Fc. 9-14. First, the capacitance, 80F, is changed to farads by dividing 80 by 1 million, since 1 million microfarads is equal to 1 farad. This quotient equals 0.000080 farad. This is substituted in the equation. 1. Xc equals 2 Fc. 1. Xc equals 2, 400, 0.000080, Xc equals 4.97. Impedance. The total opposition to current flow in an AC circuit is known as impedance, and is represented by the letter Z. The combined effects of resistance, inductive reactance, and capacitive reactance make up impedance, the total opposition to current flow in an AC circuit. In order to accurately calculate voltage and current in AC circuits, the effect of inductance and capacitance along with resistance must be considered. Impedance is measured in ohms. The rules and equations for DC circuits apply to AC circuits only when that circuit contains resistance alone, and no inductance or capacitance. In both series and parallel circuits, if an AC circuit consists of resistance only, the value of the impedance is the same as the resistance, and Ohm's law for an AC circuit, I equals E/Z, is exactly the same as for a DC circuit. Figure 9-22 illustrates a series circuit containing a heater element with 11 ohms resistance connected across a 110 volt source. To find how much current flows if 110 volts AC is applied, the following example is solved. I equals EZ, 110 V. I equals 11. I equals 10 amps. If there are two resistance values in parallel connected to an AC voltage, as seen in figure 9-23, impedance is equal to the total resistance of the circuit. Once again, the calculations would be handled the same as if it were a DC circuit, and the following would apply. RT equals 1. 1 plus 1. R1 R2. RT equals 1 1 plus 1 20 20. RT equals 10. Since this is a pure resistive circuit, RT equals Z, resistance equals impedance. ZT equals RT. ZT equals 10. To determine the current flow in the circuit, use the equation. I equals EZ, 50 V. I equals 10. I equals 5 amps. Impedance is the total opposition to current flow in an AC circuit. If a circuit has inductance or capacitance, one must take into consideration resistance, R, inductive reactance, XL, and/or capacitive reactance, XC, to determine impedance, Z. In this case, Z does not equal RT. Resistance and reactance, inductive or capacitive, cannot be added directly, but they. R equals 11. R equals 20. 110 VAC. 50 VAC power supply. A. Ammeter I equals 5A. R equals 20. I equals 10A. Figure 9-22. Ohm's law applies to AC circuit only when circuit consists of resistance only. Impedance, Z, equals resistance, R. Figure 9-23. Two resistance values in parallel connected to an AC voltage. Impedance is equal to the total resistance of the circuit. 9-15. Can be considered as two forces acting at right angles to each other. Thus, the relation between resistance, reactance, and impedance may be illustrated by a right triangle. Figure 9-24. Since these quantities may be related to the sides of a right triangle, the formula for finding the impedance can be found using the Pythagorean theorem. It states that the square of the hypotenuse is equal to the sum of the squares of the other two sides. Thus, the value of any side of a right triangle can be found if the other two sides are known. In practical terms, if a series AC circuit contains resistance and inductance, as shown in figure 9-25, the relation between the sides can be stated as Z2 equals R2 plus XLXC2. The square root of both sides of the equation gives Z equals R2 plus XLXC2. This formula can be used to determine the impedance when the values of inductive reactance and resistance are known. It can be modified to solve for impedance in circuits containing capacitive reactance and resistance by substituting XC in the formula in place of XL. In circuits containing resistance with both inductive and capacitive reactance, the reactances can be combined, but because their effects in the circuit are exactly opposite, they are combined by subtraction. The smaller number is always subtracted from the larger. Z equals XLXC, or X equals XCXL. Figure 9-25 shows example 1. Here, a series circuit containing a resistor and an inductor are connected to a source of 110 volts at 60 cycles per second. The resistive element is a simple measuring 6 ohms, and the inductive element is a reactance. Impedance XLXC. Z. R. Resistance R equals 6. 110 VAC 60 cycles. XL equals 0.021 H. A. Figure 9-25. A circuit containing resistance and inductance. Coil with an inductance of 0.021 Henry. What is the value of the impedance and the current through the circuit? Solution. First, the inductive reactance of the coil is computed. XL equals 2 times F times L. XL equals 6.28 times 60 times 0.021. XL equals 8 ohms inductive reactance. Next, the total impedance is computed. Z equals R2 plus X2. L. Z equals 62 plus A2. Z equals 36 plus 64. Z equals 100. Z equals 10. Remember, when making calculations for Z, always use inductive reactance, not inductance, and use capacitive reactance, not capacitance. Once impedance is found, the total current can be calculated. I equals EZ 110 V. I equals 10. I equals 11 amps. Since this circuit is resistive and inductive, there is a phase shift where voltage leads current. Figure 9-24. Impedance triangle. 9-16. R equals 10. Example 2 is a series circuit illustrated in which a capacitor of 200 F is connected in series with a 10 ohm resistor. Figure 9-26. What is the value of the impedance, the current flow, and the voltage drop across the resistor? Solution. First, the capacitance is changed from microfarads to farads. Since 1 million microfarads equal 1 farad, then 200 F equals 0.000200 farads. Next, solve for capacitive reactance. 1. XC equals 2 FC. 1. XC equals 260.00020. XC equals 10.07536. XC equals 13. To find the impedance, Z equals R2 plus X2. Z equals 10.2 plus 13.2. Z equals 16.4. Since this circuit is resistive and capacitive, there is a phase shift where current leads voltage. To find the current, IT equals EZ. IT equals 110 V. 6.4. IT equals 6.7 amps. To find the voltage drop across the resistor, ER. ER equals I times R. ER equals 6.78 times 10. ER equals 67 volts. To find the voltage drop over the capacitor, EC. EC equals I times XC. EC equals 6.78 times 13. EC equals 86.1 volts. The sum of these two voltages does not equal the applied voltage, since the current leads the voltage. Use the following formula to find the applied voltage. E equals ER 2 plus EC right parenthesis 2. E equals 67.2 plus 86.12. E equals 4,489 plus 7,413. E equals 11,902. E equals 110 volts. When the circuit contains resistance, inductance, and capacitance, the following equation is used to find the impedance. Z equals R2 plus XLXC 2. 110 VAC 60 cycles. C equals 200 μF. A. Figure 9-26. A circuit containing resistance and capacitance. 9-17. 4. 110 VAC 60 cycles. 7. 10. 1 2. Example 3. What is the impedance of a series circuit consisting of a capacitor with a capacitive reactance of 7 ohms, an inductor with an inductive reactance of 10 ohms, and a resistor with a resistance of 4 ohms? Figure 9-27. Solution. Z equals R2 plus XLXC 2. Z equals 4 2 plus 10 7 2. Z equals 25. Z equals 5. To find total current, ET. IT equals Z 110 V. IT equals 5. IT equals 22 amps. Remember that inductive and capacitive reactances can cause a phase shift between voltage and current. In this example, inductive reactance is larger than capacitive reactance, so the voltage leads current. It should be noted that since inductive reactance, capacitive reactance, and resistance affect each other at right angles, the voltage drops of any series AC circuit should be added using vector addition. Figure 9-28 shows the voltage drops over the series AC circuit described in example 3 above. ER equals 88 V. 110 VAC 60 cycles. EL equals 220 V. EC equals 154 V. Figure 9-28. Voltage drops. To calculate the individual voltage drops, simply use the equations. ER equals I times R. EXL equals I times XL. EXC equals I times XC. To determine the total applied voltage for the circuit, each individual voltage drop must be added using vector addition. ET equals ER. 2 plus ELEC, 2. ET equals 88 2 plus 220 154, 2. ET equals 88 2 plus 66 2. ET equals 12,100. ET equals 110 volts. Parallel AC circuits. When solving parallel AC circuits, one must also use a derivative of the Pythagorean theorem. The equation for finding impedance in an AC circuit is as follows. Z equals 1 2 plus 1 RXLXC. To determine the total impedance of the parallel circuit shown in figure 9-29, one would first determine the capacitive and inductive reactances. Remember to convert microfarads to farads. Figure 9-27. A circuit containing resistance, inductance, and capacitance. 9-18. 110 VAC 400 HZ. L equals 0.02 H. C equals 100 mu FR equals 50. IR equals 1 2 1 2. Figure 9-29. Total impedance of parallel circuit. XL equals 2 FL. XL equals 2 400 0.02. XL equals 50 1. XC equals 2 FC 100 mu F equals 0.0001 F 1. XC equals 2 400 0.0001. XC equals 4. Next, the impedance can be found. 1Z equals 1 2 plus 1 RXLXC. 1Z equals 1 2 plus 1 50 54. 1Z equals 0.02 2 plus 0.02.25 2. 1Z equals 0.0004 plus 0.0529. Z equals 1.23. Z equals 4.33. To determine the current flow in the circuit. ET, IT equals Z. IL equals IC equals 100 V. IT equals 4.33. IT equals 23.09 amps. To determine the current flow through each parallel path of the circuit, calculate IR, IL, and IC. ER, 100 V. IR equals 50. IR equals 2 amps. EXL, 100 V. IL equals 50. IL equals 2 amps. EXC, 100 V. IC equals 4. IC equals 25 amps. It should be noted that the total current flow of parallel circuits is found by using vector addition of the individual current flows as follows. IT equals I2. R plus ILIC, 2. IT equals 2 2 plus 225, 2. IT equals 2 2 plus 23 2. IT equals 4 plus 529. IT equals 533. IT equals 23 amps. 9-19. Power in AC circuits. Since voltage and current determine power, there are similarities in the power consumed by both AC and DC circuits. In AC, however, current is a function of both the resistance and the reactance of the circuit. The power consumed by any AC circuit is a function of the applied voltage, and both circuits' resistance and reactance. AC circuits have two distinct types of power, one created by the resistance of the circuit, and one created by the reactance of the circuit. True power. True power of any AC circuit is commonly referred to as the working power of the circuit. True power is the power consumed by the resistance portion of the circuit, and is measured in watts, W. True power is symbolized by the letter P, and is indicated by any wattmeter in the circuit. True power is calculated by the formula P equals I2 times Z. Apparent power. Apparent power in an AC circuit is sometimes referred to as the reactive power of a circuit. Apparent power is the power consumed by the entire circuit, including both the resistance and the reactance. Apparent power is symbolized by the letter S, and is measured in volt-amps, VA. Apparent power is a product of the effective voltage multiplied by the effective current. Apparent power is calculated by the formula S equals I2 times Z. Power factor. As seen in figure 9-30, the resistive power and the reactive power affect the circuit at right angles to each other. The power factor in an AC circuit is created by this right angle effect. Power factor can be defined as the mathematical difference between true power and apparent power. Power factor, PF, is a ratio and always a measurement between 0 and 100. The power factor is directly related to the phase shift of a circuit. The greater the phase shift of a circuit, the lower the power factor. For example, an AC circuit that is purely inductive, contains reactance only and no resistance, has a phase shift of 90 degrees, and a power factor of 0.0. An AC circuit that is purely resistive, has no reactance, has a phase shift of 0, and a power factor of 100. Power factor is calculated by using the following formula. PF equals true power, watts, times 100 apparent power, VA. Example of calculating PF. Figure 9-31 shows an AC load connected to a 50-volt power supply. The current draw of the circuit is 5 amps and the total resistance of the circuit is 8 ohms. Determine the true power, the apparent power, and the power factor for this circuit. Solution. P equals I 2 times R. P equals 5 2 times 8. P equals 200 watts. S equals E times I. S equals 50 times 5. S equals 250 VA. PF equals TP times 100. S. PF equals 200 times 100. 250. PF equals 80. Reactive power. Apparent power volts X amperes. Capacitor inductor. 50 VAC power supply. Resistor. True power. Watts. Figure 9-30. Power relations in AC circuit. 9-20. Ammeter I equals 5A. A. Figure 9-31. AC load connected to a 50 volt power supply. Power factor can also be represented as a percentage. Using a percentage to show power factor, the circuit in the previous example would have a power factor of 80%. It should be noted that a low power factor is undesirable. Circuits with a lower power factor create excess load on the power supply and produce inefficiency in the system. Aircraft AC alternators must typically operate with a power factor between 90% and 100%. It is therefore very important to carefully consider power factor when designing the aircraft electrical system. Aircraft batteries. Aircraft batteries are used for many functions, e.g., ground power, emergency power, improving DC bus stability, and fault clearing. Most small private aircraft use lead-acid batteries. Most commercial and corporate aircraft use nickel-cadmium (NiC) batteries. However, other lead-acid types of batteries are becoming available, such as the valve-regulated lead-acid (VRLA) batteries. The battery best suited for a particular application depends on the relative importance of several characteristics, such as weight, cost, volume, service or shelf life, discharge rate, maintenance, and charging rate. Any change of battery type may be considered a major alteration. Types of batteries. Aircraft batteries are usually identified by the material used for the plates. The two most common types of battery used are lead-acid and NiC batteries. Lead-acid batteries. Dry charged cell lead-acid batteries. Dry charged cell lead-acid batteries, also known as flooded or wet batteries, are assembled with electrodes, plates, that have been fully charged and dried. The electrolyte is added to the battery when it is placed in service, and battery life begins when the electrolyte is added. An aircraft storage battery consists of 6 or 12 lead-acid cells connected in series. The open circuit voltage of the 6-cell battery is approximately 12 volts, and the open circuit voltage of the 12-cell battery is approximately 24 volts. Open circuit voltage is the voltage of the battery when it is not connected to a load. When flooded, vented, batteries are on charge, the oxygen generated at the positive plates escapes from the cell. Concurrently, at the negative plates, hydrogen is generated from water and escapes from the cell. The overall result is the gassing of the cells and water loss. Therefore, flooded cells require periodic water replenishment. Figure 9-32. Figure 9-32. Lead-acid battery installation. Valve-regulated lead-acid batteries, VRLA. VRLA batteries contain all electrolyte absorbed in glass mat separators with no free electrolyte, and are sometimes referred to as sealed batteries. Figure 9-33. The electrochemical reactions for VRLA batteries are the same as flooded batteries, except for the gas recombination mechanism that is predominant in VRLA batteries. These types of battery are used in general aviation and turbine-powered aircraft, and are sometimes authorized replacements for NiC batteries. When VRLA batteries are on charge, oxygen combines chemically with the lead at the negative plates in the presence of H2SO4 to form lead sulfate and water. This oxygen recombination suppresses the generation of hydrogen at the negative plates. Overall, there is no water loss during charging. A very small quantity of water may be lost as a result of self-discharge reactions. However, such loss is so small that no provisions are made for water replenishment. The battery cells have a pressure relief safety valve that may vent if the battery is overcharged. Figure 9-33. Valve-regulated lead-acid battery, sealed battery. 9-21. NiC batteries. A NiC battery consists of a metallic box, usually stainless steel, plastic-coated steel, painted steel, or titanium containing a number of individual cells. Figure 9-34. These cells are connected in series to obtain 12 volts or 24 volts. The cells are connected by highly conductive nickel-copper links. Inside the battery box, the cells are held in place by partitions, liners, spacers, and a cover assembly. The battery has a ventilation system to allow the escape of the gases produced during an overcharged condition and provide cooling during normal operation. NiC cells installed in an aircraft battery are typical of the vented cell type. The vented cells have a vent, or low-pressure release valve that releases any generated oxygen and hydrogen gases when overcharged or discharged rapidly. This also means the battery is not normally damaged by excessive rates of overcharge, discharge, or even negative charge. The cells are rechargeable and deliver a voltage of 1.2 volts during discharge. Aircraft that are outfitted with NiC batteries typically have a fault protection system that monitors the condition of the battery. The battery charger is the unit that monitors the condition of the battery, and the following conditions are monitored. 1. Overheat condition. 2. Low temperature condition, below 40 degrees F. 3. Cell imbalance. 4. Open circuit. 5. Shorted circuit. If the battery charger finds a fault, it turns off and sends a fault signal to the electrical load management system, ELMS. NIC batteries are capable of performing to its rated capacity when the ambient temperature of the battery is in the range of approximately 60-90 degrees F. An increase or decrease in temperature from this range results in reduced capacity. NIC batteries have a ventilation system to control the temperature of the battery. A combination of high battery temperature in excess of 160 degrees F and overcharging can lead to a condition called thermal runaway. Figure 9-35. The temperature of the battery has to be constantly monitored to ensure safe operation. Thermal runaway can result in a NIC chemical fire and/or explosion of the NIC battery under recharge by a constant voltage source and is due to cyclical, ever-increasing temperature and charging current. One or more shorted cells or an existing high temperature and low charge can produce the following cyclical sequence of events. 1. Excessive current. 2. Increased temperature. 3. Decreased cells resistance. 4. Further increased current. And 5. Further increased temperature. This does not become a self-sustaining thermal-chemical action if the constant voltage charging source is removed before the battery temperature is in excess of 160 degrees F. Capacity. Capacity is measured quantitatively in ampere hours delivered at a specified discharge rate to a specified cutoff voltage at room temperature. The cutoff voltage is 1.0 volt per cell. Battery available capacity depends upon several factors including such items as 1. Cell design, cell geometry, plate thickness, hardware, and terminal design govern performance under specific usage conditions of temperature, discharge rate, EG. Figure 9-34. NIC battery installation. Figure 9-35. Thermal runaway damage. 9-22. 2. Discharge rate, high current rates yield less capacity than low rates. 3. Temperature, capacity and voltage levels decrease as battery temperature moves away from the 60 degrees F, 16 degrees C, to 90 degrees F, 32 degrees C, range toward the high and low extremes. 4. Charge rate, higher charge rates generally yield greater capacity. Aircraft battery ratings by specification. The 1-hour rate is the rate of discharge a battery can endure for 1 hour with the battery voltage at or above 1.67 volts per cell, or 20 volts for a 24-volt lead-acid battery, or 10 volts for a 12-volt lead-acid battery. The 1-hour capacity, measured in ampere hours, is the product of the discharge rate and time, in hours, to the specified end voltage. The emergency rate is the total essential load, measured in amperes, required to support the essential bus for 30 minutes. This is the rate of discharge a battery can endure for 30 minutes with the battery voltage at or above 1.67 volts per cell, or 20 volts for a 24-volt lead-acid battery, or 10 volts for a 12-volt lead-acid battery. Storing and servicing facilities. Separate facilities for storing and/or servicing flooded electrolyte lead-acid and NIC batteries must be maintained. Introduction of acid electrolyte into alkaline electrolyte causes permanent damage to vented, flooded electrolyte, NIC batteries and vice versa. However, batteries that are sealed can be charged and capacity checked in the same area. Because the electrolyte in a valve-regulated lead-acid battery is absorbed in the separators and porous plates, it cannot contaminate a NIC battery even when they are serviced in the same area. Warning: it is extremely dangerous to store or service lead-acid and NIC batteries in the same area. Introduction of acid electrolytes into alkaline electrolyte destroys the NIC, and vice versa. Battery freezing. Discharged lead-acid batteries exposed to cold temperatures are subject to plate damage due to freezing of the electrolyte. To prevent freezing damage, maintain each cell's specific gravity at 1.275 or, for sealed lead-acid batteries, check open circuit voltage. Figure 9-36. NIC battery electrolyte is not as susceptible to freezing, because no appreciable chemical change takes place between the charged and discharged states. However, the electrolyte freezes at approximately 75 degrees F. Freezing point specific gravity. State of charge, SOC, for sealed lead-acid batteries at 70 degrees. 1.300, 1.275. 1.250, 1.225, 1.200, 1.175, 1.150, 1.125, 1.100, degrees C 70, 62, 52, 37, 26, 20, 15, 10, 08, degrees F 95, 80, 62, 35, 16, 04, plus 05, plus 13, plus 19. SOC 100%, 75%, 50%, 25%, 12 volt, 12.9, 12.7, 12.4, 12.0, 24 volt, 25.8, 25.4, 24.8, 24.0. Figure 9-36. Lead-acid battery electrolyte freezing points. Note: only a load check determines overall battery condition. Temperature correction. US manufactured lead-acid batteries are considered fully charged when the specific gravity reading is between 1.275 and 1.300. A 1,3 discharged battery reads about 1.240, and a 2,3 discharged battery shows a specific gravity reading of about 1.200 when tested by a hydrometer at an electrolyte temperature of 80 degrees F. However, to determine precise specific gravity readings, a temperature correction should be applied to the hydrometer indication. Figure 9-37 is an example. For a hydrometer reading of 1.260 and electrolyte temperature of 40 degrees F, the corrected specific gravity reading of the electrolyte is 1.244. Electrolyte temperature. Points to subtract from or add to specific gravity readings. Degrees C plus 60, plus 55, plus 49, plus 43, plus 38, plus 33, plus 27, plus 23, plus 15, plus 10, plus 05, 02, 07, 13, 18, 23, 28, 35. Degrees F plus 140, plus 130, plus 120, plus 110, plus 100, plus 90, plus 80, plus 70, plus 60, plus 50, plus 40, plus 30, plus 20, plus 10, 0, 10, 20, 30, 12 volt plus 0.024, plus 0.020, plus 0.016, plus 0.012, plus 0.008, plus 0.004, 0, 0.004, 0.008, 0.012, 0.016, 0.020, 0.024, 0.028, 0.032, 0.036, 0.040, 0.044. Figure 9-37. Sulfuric acid temperature correction. 9-23. Battery charging. Operation of aircraft batteries beyond their ambient temperature or charging voltage limits can result in excessive cell temperatures leading to electrolyte boiling, rapid deterioration of the cells, and battery failure. The relationship between maximum charging voltage and the number of cells in the battery is also significant. This determines, for a given ambient temperature and state of charge, the rate at which energy is absorbed as heat within the battery. For lead-acid batteries, the voltage per cell must not exceed 2.35 volts. In the case of NiC batteries, the charging voltage limit varies with design and construction. Values of 1.4 and 1.5 volts per cell are generally used. In all cases, follow the recommendations of the battery manufacturer. Constant voltage charging, CP. The battery charging system in an airplane is of the constant voltage type. An engine-driven generator, capable of supplying the required voltage, is connected through the aircraft electrical system directly to the battery. A battery switch is incorporated in the system so that the battery may be disconnected when the airplane is not in operation. The voltage of the generator is accurately controlled by means of a voltage regulator connected in the field circuit of the generator. For a 12-volt system, the voltage of the generator is adjusted to approximately 14.25. On 24-volt systems, the adjustment should be between 28 and 28.5 volts. When these conditions exist, the initial charging current through the battery is high. As the state of charge increases, the battery voltage also increases, causing the current to taper down. When the battery is fully charged, its voltage is almost equal to the generator voltage, and very little current flows into the battery. When the charging current is low, the battery may remain connected to the generator without damage. When using a constant voltage system in a battery shop, a voltage regulator that automatically maintains a constant voltage is incorporated in the system. A higher capacity battery, e.g., 42Ah, has a lower resistance than a lower capacity battery, e.g., 33Ah. Hence, a high capacity battery draws a higher charging current than a low capacity battery when both are in the same state of charge, and when the charging voltages are equal. The constant voltage method is the preferred charging method for lead-acid batteries. Constant current charging. Constant current charging is the most convenient for charging batteries outside the airplane, because several batteries of varying voltages may be charged at once on the same system. A constant current charging system usually consists of a rectifier to change the normal AC supply to DC. A transformer is used to reduce the available 110 volt or 220 volt AC supply to the desired level before it is passed through the rectifier. If a constant current charging system is used, multiple batteries may be connected in series, provided that the charging current is kept at such a level that the battery does not overheat or gas excessively. The constant current charging method is the preferred method for charging NiC batteries. Typically, a NiC battery is constant current charged at a rate of 1 ca until all the cells have reached at least 1.55 V. Another charge cycle follows at 0.1 ca, again until all cells have reached 1.55 V. The charge is finished with an overcharge or top-up charge, typically for not less than 4 hours at a rate of 0.1 ca. The purpose of the overcharge is to expel as much, if not all the gases collected on the electrodes, hydrogen on the anode, and oxygen on the cathode. Some of these gases recombine to form water that, in turn, raises the electrolyte level to its highest level, after which it is safe to adjust the electrolyte levels. During the overcharge, or top-up charge, the cell voltages go beyond 1.6 V, and then slowly start to drop. No cell should rise above 1.71 V, dry cell, or drop below 1.55 V, gas barrier broken. Charging is done with vent caps loosened or open. A stuck vent might increase the pressure in the cell. It also allows for refilling of water to correct levels before the end of the top-up charge, while the charge current is still on. However, cells should be closed again as soon as the vents have been cleaned and checked, since carbon dioxide dissolved from outside air carbonates the cells and ages the battery. Battery maintenance. Battery inspection and maintenance procedures vary with the type of chemical technology and the type of physical construction. Always follow the battery manufacturer's approved procedures. Battery performance at any time in a given application depends upon the battery's age, state of health, state of charge, and mechanical integrity, which you can determine according to the following. To determine the life and age of the battery, record the install date of the battery on the battery. During normal battery maintenance, battery age must be documented either in the aircraft maintenance log or in the shop maintenance log. Lead-acid battery state of health may be determined by duration of service interval in the case of vented batteries, by environmental factors such as excessive heat or cold, and by observed electrolyte leakage, as evidenced by corrosion of wiring and connectors or accumulation of powdered salts. If the battery needs to be refilled often, with no evidence of external leakage, this may indicate a poor state of the battery charging system, or an overcharge condition. 9-24. Use a hydrometer to determine the specific gravity of the lead-acid battery electrolyte, which is the weight of the electrolyte compared to the weight of pure water. Take care to ensure the electrolyte is returned to the cell from which it was extracted. When a specific gravity difference of 0.050 or more exists between cells of a battery, the battery is approaching the end of its useful life and replacement should be considered. Electrolyte level may be adjusted by the addition of distilled water. Do not add electrolyte. Battery state of charge is determined by the cumulative effect of charging and discharging the battery. In a normal electrical charging system, the aircraft generator or alternator restores a battery to full charge during a flight of 1 hour to 90 minutes. Proper mechanical integrity involves the absence of any physical damage, as well as assurance that hardware is correctly installed and the battery is properly connected. Battery and battery compartment venting system tubes, nipples, and attachments, when required, provide a means of avoiding the potential buildup of explosive gases, and should be checked periodically to ensure that they are securely connected and oriented in accordance with the maintenance manual's installation procedures. Always follow procedures approved for the specific aircraft and battery system to ensure that the battery system is capable of delivering specified performance. Battery and charger characteristics. The following information is provided to acquaint the user with characteristics of the more common aircraft battery and battery charger types. Figure 9-38 products may vary from these descriptions due to different applications of available technology. Consult the manufacturer for specific performance data. Note: never connect a lead-acid battery to a charger unless properly serviced. Lead-acid batteries. Lead-acid vented batteries have a 2-volt nominal cell voltage. Batteries are constructed so that individual cells cannot be removed. Occasional addition of water is required to replace water lost due to overcharging in normal service. Batteries that become fully discharged may not accept recharge. Lead-acid sealed batteries are similar in most respects to lead-acid vented batteries, but do not require the addition of water. The lead-acid battery is economical and has extensive application, but is heavier than an equivalent performance battery of another type. The battery is capable of a high rate of discharge and low temperature performance. However, maintaining a high rate of discharge for a period of time usually warps the cell plates, shorting out the battery. Its electrolyte has a moderate specific gravity, and state of charge can be checked with a hydrometer. Lead-acid batteries are usually charged by regulated DC voltage sources. This allows maximum accumulation of charge in the early part of recharging. NIC batteries. NIC vented batteries have a 1.2 volt nominal cell voltage. Occasional addition of distilled water is required to replace water lost due to overcharging in normal service. Cause of failure is usually shorting or weakening of a cell. After replacing the bad cell with a good cell, the battery's life can be extended for 5 or more years. Full discharge is not harmful to this type of battery. NIC-sealed batteries are similar in most respects to NIC-vented batteries, but do not normally require the addition of water. Fully discharging the battery to 0 volts may cause irreversible damage to 1 or more cells, leading to eventual battery failure due to low capacity. The state of charge of a NIC battery cannot be determined by measuring the specific gravity of the potassium hydroxide electrolyte. The electrolyte specific gravity does not change with the state of charge. The only accurate way to determine the state of charge of a NIC battery is by a measured discharge with a NIC battery charger and following the manufacturer's instructions. After the battery has been fully charged and allowed to stand for at least 2 hours, the fluid level may be adjusted, if necessary, using distilled or demineralized water. Because the fluid level varies with a Figure 9-38. Battery charger. 9-25. State of charge. Water should never be added while the battery is installed in the aircraft. Overfilling the battery results in electrolyte spillage during charging. This causes corrosive effects on the cell links, self-discharge of the battery, dilution of the electrolyte density, possible blockage of the cell vents, and eventual cell rupture. Constant current battery chargers are usually provided for NIC batteries because the NIC cell voltage has a negative temperature coefficient. With a constant voltage charging source, a NIC battery having a shorted cell might overheat due to excessive overcharge and undergo a thermal runaway, destroying the battery and creating a possible safety hazard to the aircraft. Pulse current battery chargers are sometimes provided for NIC batteries. Caution: it is important to use the proper charging procedures for batteries under test and maintenance. These charging regimes for reconditioning and charging cycles are defined by the aircraft manufacturer and should be closely followed. Aircraft battery inspection. Aircraft battery inspection consists of the following items. 1. Inspect battery sump jar and lines for condition and security. 2. Inspect battery terminals and quickly disconnect plugs and pins for evidence of corrosion, hitting, arcing, and burns. Clean as required. 3. Inspect battery drain and vent lines for restriction, deterioration, and security. 4. Routine pre-flight and post-flight inspection procedures should include observation for evidence of physical damage, loose connections, and electrolyte loss. Ventilation systems. Modern airplanes are equipped with battery ventilating systems. The ventilating system removes gases and acid fumes from the battery in order to reduce fire hazards and to eliminate damage to airframe parts. Air is carried from a scoop outside the airplane through a vent tube to the interior of the battery case. After passing over the top of the battery, air, battery gases, and acid fumes are carried through another tube to the battery sump. This sump is a glass or plastic jar of at least 1 pint capacity. In the jar is a felt pad about 1 inch thick saturated with a 5% solution of bicarbonate of soda and water. The tube carrying fumes to the sump extends into the jar to within about 1/4 inch of the felt pad. An overboard discharge tube leads from the top of the sump jar to a point outside the airplane. The outlet for this tube is designed so there is negative pressure on the tube whenever the airplane is in flight. This helps to ensure a continuous flow of air across the top of the battery through the sump and outside the airplane. The acid fumes going into the sump are neutralized by the action of the soda solution, thus preventing corrosion of the aircraft's metal skin or damage to a fabric surface. Installation practices. External surface. Clean the external surface of the battery prior to installation in the aircraft. Replacing lead-acid batteries. When replacing lead-acid batteries with NIC batteries, a battery temperature or current monitoring system must be installed. Neutralize the battery box or compartment and thoroughly flush with water and dry. A flight manual supplement must also be provided for the NIC battery installation. Acid residue can be detrimental to the proper functioning of a NIC battery, as alkaline is to a lead-acid battery. Battery venting. Battery fumes and gases may cause an explosive mixture or contaminated compartments, and should be dispersed by adequate ventilation. Venting systems often use ram pressure to flush fresh air through the battery case or enclosure to a safe overboard discharge point. The venting system pressure differential should always be positive, and remain between recommended minimum and maximum values. Line runs should not permit battery overflow fluids or condensation to be trapped, and prevent free airflow. Battery sump jars. A battery sump jar installation may be incorporated in the venting system to dispose of battery electrolyte overflow. The sump jar should be of adequate design, and the proper neutralizing agent used. The sump jar must be located only on the discharge side of the battery venting system. Installing batteries. When installing batteries in an aircraft, exercise care to prevent inadvertent shorting of the battery terminals. Serious damage to the aircraft structure, frame, skin and other subsystems, avionics, wire, fuel, egg, can be sustained by the resultant high discharge of electrical energy. This condition may normally be avoided by insulating the terminal posts during the installation process. Remove the grounding lead first for battery removal, then the positive lead. Connect the grounding lead of the battery last to minimize the risk of shorting the hot terminal of the battery during installation. Battery hold-down devices. Ensure that the battery hold-down devices are secure, but not so tight as to 9-26. Exert excessive pressure that may cause the battery to buckle, causing internal shorting of the battery. Quick disconnect type battery. If a quick disconnect type of battery connector that prohibits crossing the battery lead is not employed, ensure that the aircraft wiring is connected to the proper battery terminal. Reverse polarity in an electrical system can seriously damage a battery and other electrical components. Ensure that the battery cable connections are tight to prevent arcing or a high resistance connection. Troubleshooting. See figure 9-39 for a troubleshooting chart. DC generators and controls. DC generators transform mechanical energy into electrical energy. As the name implies, DC generators produce direct current and are typically found on light aircraft. In many cases, DC generators have been replaced with DC alternators. Both devices produce electrical energy to power the aircraft's electrical loads and charge the aircraft's battery. Even though they share the same purpose, the DC alternator and DC generator are very different. DC generators require a control circuit in order to ensure the generator maintains the correct voltage and current for the current electrical conditions of the aircraft. Typically, aircraft generators maintain a nominal output voltage of approximately 14 volts or 28 volts. Generators. The principles of electromagnetic induction were discussed earlier in this chapter. These principles show that voltage is induced in the armature of a generator throughout the entire 360 degrees rotation of the conductor. The armature is the rotating portion of a DC generator. As shown, the voltage being induced is AC. Figure 9-40. Since the conductor loop is constantly rotating, some means must be provided to connect this loop of wire to the electrical loads. As shown in figure 9-41, slip rings and brushes can be used to transfer the electrical energy from the rotating loop to the stationary aircraft loads. The slip rings are connected to the loop and rotate, the brushes are stationary and allow a current path to the electrical loads. The slip rings are typically a copper material and the brushes are a soft carbon substance. It is important to remember that the voltage being produced by this basic generator is AC, and AC voltage is supplied to the slip rings. Since the goal is to supply DC loads, some means must be provided to change the AC voltage to a DC voltage. Generators use a modified slip ring arrangement, known as a commutator, to change the AC produced in the generator loop into a DC voltage. The action of the commutator allows the generator to produce a DC output. By replacing the slip rings of the basic AC generator with two half cylinders, the commutator, a basic DC generator, is obtained. In figure 9-42, the red side of the coil is connected to the red segment and the amber side of the coil to the amber segment. The segments are insulated from each other. The two stationary brushes are placed on opposite sides of the commutator and are so mounted that each brush contacts each segment of the commutator as the commutator revolves simultaneously with the loop. The rotating parts of a DC generator, coil and commutator, are called an armature. As seen in the very simple generator of figure 9-42, as the loop rotates, the brushes make contact with different segments of the commutator. In positions A, C, and D, the brushes touch the insulation between the brushes. When the loop is in these positions, no voltage is being produced. In position B, the positive brush touches the red side of the conductor loop. In position D, the positive brush touches the amber side of the armature conductor. This type of connection reversal changes the AC produced in the conductor coil into DC to power the aircraft. An actual DC generator is more complex, having several loops of wire and commutator segments. Because of this switching of commutator elements, the red brush is always in contact with the coil side moving downward, and the amber brush is always in contact with the coil side moving upward. Though the current actually reverses its direction in the loop in exactly the same way as in the AC generator, commutator action causes the current to flow always in the same direction through the external circuit or meter. The voltage generated by the basic DC generator in figure 9-42 varies from 0 to its maximum value twice for each revolution of the loop. This variation of DC voltage is called ripple and may be reduced by using more loops, or coils, as shown in figure 9-43. As the number of loops is increased, the variation between maximum and minimum values of voltage is reduced. Figure 9-43, and the output voltage of the generator approaches a steady DC value. For each additional loop in the rotor, another 2 commutator segments is required. A photo of a typical DC generator commutator is shown in figure 9-44, 9-27. Check and correct external circuitry. Clean battery, charge, and adjust electrolyte level. Trouble probable cause corrective action. Apparent loss of capacity very common when recharging on a constant potential bus, as an aircraft. Usually indicates imbalance between cells because of difference in temperature, charge efficiency, self-discharge rate, EC, in the cells. Electrolyte level too low, battery not fully charged. Reconditioning will alleviate this condition. Charge. Adjust electrolyte level. Check aircraft voltage regulator. If OK, reduce maintenance interval. Complete failure to operate defective connection and equipment circuitry in which battery is installed, such as broken LED, inoperative relay, or improper receptacle installation. N-terminal connector loose or damaged poor inter-cell connections. Open circuit or dry cell. Clean and retighten hardware using proper torque values. Replace defective cell. Excessive spewage of electrolyte, high charge voltage, high temperature during charge, electrolyte level too high. Loose or damaged vent cap. Damaged cell and seal. Clean battery, tighten or replace cap, charge and adjust electrolyte level. Short out all cells to 0 volts. Clean battery, replace defective cell, charge, and adjust electrolyte level. Failure of one or more cells to rise to the required 1.55 volts at the end of charge. Negative electrode not fully charged, cellophane separator damaged. Foreign material within the cell case introduced into cell through addition of impure water or water contaminated with acid. Discharge battery and disassemble, remove cell and replace, recondition battery. Discharge battery and recharge. If the cell still fails to rise to 1.55 volts, or if the cell's voltage rises to 1.55 volts, or above and then drops, remove cell and replace. Distortion of cell case to cover overcharged, over-discharged, or overheated cell with internal short. Plugged vent cap, overheated battery. Discharge battery and disassemble. Replace defective cell. Recondition battery. Replace vent cap. Check voltage regulator. Treat battery as above, replacing battery case and cover and all other defective parts. Frequent addition of water cell out of balance damaged O-ring. Vent cap leaking cell. Charge voltage too high. Recondition battery. Replace damaged parts. Discharge battery and disassemble. Replace defective cell. Recondition battery. Adjust voltage regulator. Erosion of top hardware, acid fumes, or spray or other corrosive atmosphere. Replace parts. Battery should be kept clean and kept away from such environments. Figure 9-39. Battery troubleshooting guide. 9-28. Trouble probable cause corrective action. Discolored or burned end connectors or intercell connectors. Dirty connections, loose connection, improper mating of parts. Clean parts. Replace if necessary. Retighten hardware using proper torque values. Check to see that parts are properly mated. Distortion of battery case and door cover explosion caused by dry cells, charger failure, high charge voltage, plugged vent caps, loose intercell connectors. Discharge battery and disassemble. Replace damaged parts and recondition. Figure 9-39. Battery troubleshooting guide. Continued. Voltage plus voltage. Maximum. 1 cycle. Minimum. 0 degrees. 90 degrees, 270 degrees, 360 degrees. 180 degrees. B. Maximum. SN. A. Figure 9-40. Output of an elementary generator. Instruction features of DC generators. The major parts, or assemblies, of a DC generator are a field frame, a rotating armature, and a brush assembly. The parts of a typical aircraft generator are shown in Figure 9-45. Field frame. The frame has two functions: to hold the windings needed to produce a magnetic field, and to act as a mechanical support for the other parts of the generator. The actual electromagnet conductor is wrapped around pieces of laminated metal called field poles. The poles are typically bolted to the inside of the Figure 9-41. Generator slip rings and loop rotate. Brushes are stationary. Frame and laminated to reduce eddy current losses, and serve the same purpose as the iron core of an electromagnet. They concentrate the lines of force produced by the field coils. The field coils are made up of many turns of insulated wire, and are usually wound on a form that fits over the iron core of the pole to which it is securely fastened. Figure 9-46. A BCDE. Induced EMF. 1 revolution. Figure 9-42. A two-piece slip ring, or commutator, allows brushes to transfer current that flows in a single direction, DC. 9-29. SN. A BCDE. Induced EMF. Figure 9-44. Typical DC generator commutator. 0 and 1/4, 1/2 and 3/4, 1. Revolutions, B. Figure 9-43. Increasing the number of coils reduces the ripple in the voltage. A DC current is fed to the field coils to produce an electromagnetic field. This current is typically obtained from an external source that provides voltage and current regulation for the generator system. Generator control systems are discussed later in this chapter. Armature. The armature assembly of a generator consists of two primary elements: the wire coils, called windings, wound around an iron core, and the commutator assembly. The armature windings are evenly spaced around the armature and mounted on a steel shaft. The armature rotates inside the magnetic field produced by the field coils. The core of the armature acts as an iron conductor in the magnetic field and, for this reason, is laminated to prevent the circulation of eddy currents. A typical armature assembly is shown in Figure 9-47. Connector lugs, field frame, drive end frame. Seal ball bearings. Air scoop. Brush connector bars. Commutator. Steel ring. Drive shaft. Commutator end frame. Brush and holder. Hole shoe screw, field winding. Field frame. Armature drive end. Figure 9-45. Typical 24-volt aircraft generator. 9-30. Commutator. Shaft. Coils. Figure 9-46. Generator field frame. Figure 9-47. A drum-type armature. Commutators. Figure 9-48 shows a cross-sectional view of a typical commutator. The commutator is located at the end of an armature and consists of copper segments divided by a thin insulator. The insulator is often made from the mineral mica. The brushes ride on the surface of the commutator, forming the electrical contact between the armature coils and the external circuit. A flexible, braided copper conductor, commonly called a pigtail, connects each brush to the external circuit. The brushes are free to slide up and down in their holders, in order to follow any irregularities in the surface of the commutator. The constant making and breaking of electrical connections between the brushes and the commutator segments, along with the friction between the commutator and the brush, causes brushes to wear out and need regular attention or replacement. For these reasons, the material commonly used for brushes is high-grade carbon. The carbon must be soft enough to prevent undue wear of the commutator, and yet hard enough to provide reasonable brush life. Since the contact resistance of carbon is fairly high, the brush must be quite large to provide a current path for the armature windings. The commutator surface is highly polished to reduce friction as much as possible. Oil or grease must never be used on A. Commutator bars. Mica insulation between bars. Tightening nut. Iron ring. Mica V-ring. Front V-ring. Commutator bar. Mica. Iron shell. Slots back V-ring with mica inner and outer rings for insulation. Figure 9-48. Commutator with portion removed to show construction. 9-31. Commutator, and extreme care must be used when cleaning it to avoid marring or scratching the surface. Types of DC generators. There are 3 types of DC generators: series wound, parallel, shunt, wound, and series parallel, or compound wound. The appropriate generator is determined by the connections to the armature and field circuits with respect to the external circuit. The external circuit is the electrical load powered by the generator. In general, the external circuit is used for charging the aircraft battery and supplying power to all electrical equipment being used by the aircraft. As their names imply, windings in series have characteristics different from windings in parallel. Series wound DC generators. The series generator contains a field winding connected in series with the external circuit. Figure 9-49. Series generators have very poor voltage regulation under changing load. Since the greater the current is through the field coils to the external circuit, the greater the induced EMFs, and the greater the output voltage is. When the aircraft electrical load is increased, the voltage increases. When the load is decreased, the voltage decreases. Since the series wound generator has such poor voltage and current regulation, it is never employed as an airplane generator. Generators in airplanes have field windings, and are connected either in shunt or in compound formats. Parallel, shunt, wound DC generators. A generator having a field winding connected in parallel with the external circuit is called a shunt generator. Figure 9-50. It should be noted that, in electrical terms, shunt means field rheostat. Field winding, SN, plus, load. Figure 9-49. Diagram of a series wound generator. A. Field winding, field rheostat. Armature winding, load, SN, plus, shunt circuit main circuit. B. Field coils armature. Figure 9-50. Shunt wound generator, parallel. Therefore, this type of generator could be called either a shunt generator or a parallel generator. In a shunt generator, any increase in load causes a decrease in the output voltage, and any decrease in load causes an increase output voltage. This occurs since the field winding is connected in parallel to the load and armature, and all the current flowing in the external circuit passes only through the armature winding, not the field. As shown in figure 9-50A, the output voltage of a shunt generator can be controlled by means of a rheostat inserted in series with the field windings. As the resistance of the field circuit is increased, the field current is reduced. Consequently, the generated voltage is also reduced. As the field resistance is decreased, the field current increases and the generator output increases. In the actual aircraft, the field rheostat would be replaced with an automatic control device, such as a voltage regulator. Compound wound DC generators. A compound wound generator employs 2 field windings, one in series, and another in parallel with the load. Figure 9-51. This arrangement takes advantage of both the series and 9-32.